Now, a key aspect of this example where we are throwing a fair cubical die 4 times is that each individual throw will be independent of the others. We can tell just by imagining doing the experiment ourselves. So you don't actually see the word independent in the text of the question, but by thinking about it, we know each throw will not affect the other throws. So each throw will be independent. For that reason, we can use the result that the probability of A and B happening, if A and B are independent, is simply the probability that A happens times the probability that B happens. So let's apply this to part A. Each throw gives an even score. So this is the probability that the first throw is even, and the second throw is even, and the third one is even, and the fourth also even. Once again, because the throws are independent, we can simply multiply their probabilities together. So this is the probability of getting an even score multiplied by itself, multiplied by itself, multiplied by itself. In other words, the probability of an even score to the power 4. And if it's a normal cubical die, then there are 3 even numbers on the die out of 6 altogether. So this is 1/2, well, 3/6 cancels down to a half to the power 4. So it's 1/16. In part B, we want the probability that at least 1/6 is thrown. The probability 1 or more 6s. So that could be 2 6s, or 3 6s, or 4 6s, or 1 6, of course. The only outcome we don't want here is 0 6s. So it's going to be quicker to work out the probability of getting 0 6s and take that away from 1, because it's the only outcome that we don't want. Same as part A, each roll will be independent, so we can simply multiply each probability by itself. So not getting a 6 on the first throw is 5/6, and on the second throw, again 5/6, 5/6 on the third, 5/6 on the fourth. Again, we can times them by themselves because we know these rolls are going to be independent of each other. So that turns out to be 671/1296.